All right, guys, welcome to lesson 4 of unit 5. We're going to introduce you guys to something today called the first derivative test. And what that does is it helps you find where the relative extrema are. And not just where they are, but also whether they're a max or a min. And that has a lot to do with the candidates test, right? The candidates test is a way to find where the absolute extrema are. So the first derivative test is similar, but instead of absolute, it's for finding relative. And the processes are also a little bit similar, but there are some differences. So I do want to take some time to compare and contrast those two tests at some point as well. So let's go ahead and begin here. In section 5.1, we learned how to find where relative extrema are located, and they're located at those critical values. Those are the places where the derivative is 0 or undefined, right? But what it didn't tell us was it didn't tell us whether those relative extrema were maxes or mins, and that's what the first derivative test will help us do. In section 5.2, we learned how to find the absolute extrema using the candidates test, and so today we're going to learn the first derivative test, which helps us not only know where the relative extrema are, but what kind of relative extrema they are. So, the first derivative test is a process we use to determine if a relative extrema is a max or a min. And we do this by looking at the slopes around the critical values. Because remember, once again, the critical values tell us where they are, but by looking at the slopes around the critical values, we can tell what kind they are. So first of all, let's do some basic review here. Now, on the left side of this graph that I've got here, that line is going in a downward direction. And so in that case, we would say that on that interval, f prime is negative, right? Because the f prime is the slope, and since the graph is going in a downward direction, we would say that on that part of our graph, the slope is negative, and therefore the derivative is negative. Now let's take a look at the right side of our graph. Over here, it's the opposite, right? It's going in an upward direction, and that means that the slope is positive, and therefore on this interval my derivative is positive. So I'm going to put greater than 0 on this side, and on this side over here I'm going to put less than 0. Greater than 0 means positive, less than 0 means negative. Okay, and then we have here in the middle area a flat line, and those areas have flat slopes which have 0 slopes. So that means that the derivative is 0 on this interval. Okay, so just kind of keep those things in mind. That will come in handy for what we're going to discuss in just a moment. So let's take a look at this. Let me move my little thing down here so you can see the entire screen. Just a moment. Okay, there we go. Now, this is basically the first derivative test in a nutshell here. So let's take a look at it. Notice that right here would be a critical value. Why? Because the slope is 0 there. That's where I would have a flat tangent line. So that tells me that at that point I either have a relative min or a relative max. Now you guys know that this is a relative minimum, right? Just by looking. But let's look at the left. Whenever you have a relative minimum, on the left the slope is negative, and on the right the slope is positive. If you have a relative maximum, so if your critical value is up here, and the slope on the left is positive and the slope on the right is negative, the opposite, then that means you have a relative max. So if f prime changes from negative to positive, like in this case here, negative slope, 0 slope, positive slope, that means you have a relative minimum. But if f prime changes from positive to negative, positive slope, 0 slope, negative slope, that means you have a relative maximum. Okay? So that is basically what the first derivative test is. Now, there are cases where the slope doesn't change. So consider this, for instance. Like in this case, my critical value would be here because that's where the slope is 0. Now, to the left, it's positive, and to the right, it's positive. Well, it didn't change. It didn't go from positive to negative, and it didn't go from negative to positive. It just went from positive to more positive. And because of that, this is not a relative extrema. It's still a critical value, because remember, critical values have slopes that are 0. But critical values are not always relative and extrema. And in this case, this is an example of one that's not a relative extrema. So, same thing over here, critical value here, but the slope goes from negative to negative. So, no change in the signs. So, if the derivative does not change signs at that critical value, x equals c, then f of c is not a relative extrema. Okay? All right, now this looks terrible, doesn't it? That's a lot to look at. Let's go ahead and cover some of this up so it's not so overwhelming. We'll go through it one at a time. All right, so how do we do the first derivative test to determine if a relative extrema is a max, min, or neither? Maybe a better way to have worded this would be as follows. There, I changed it. How to use the first derivative test to determine if a critical value gives us a relative max, a relative min, or neither. Okay. So, first of all, the first thing we're going to do is we want to see if there's any discontinuities. If you have a discontinuity, you want to rule those out at the very beginning. If you have it, because at a discontinuity, that will give you a critical value, but a discontinuity cannot be a relative extrema. So if you have any discontinuities on your function, then we're going to start right away and just say, oh, that's neither. It's not a relative min or a max. Okay. But the second step is we're going to find the rest of the critical values. So we're going to look for those places where the derivative is 0 or where the derivative is undefined. And remember, we want to exclude any of the discontinuities that we found in step 1 because they're not going to matter. Let's go ahead and take a look at step 3. Once you know where all your critical values are, we're going to write out some test intervals. Okay, it's kind of like the number line test that we did earlier with absolute value functions. We're going to pick some test points in that interval. We're going to plug them into our derivative, and we're going to see, does our derivative come out positive or negative on that interval? If it's positive, that would indicate that it's sloping up. If it's negative, that would mean it's sloping down. Okay? Based on what it's doing, then we could decide whether it's a relative max or a min. In the end, you might, depending on what the question is asking, if it's asking you to find the max or min, then you're going to need to plug those x values in to find the y values, because it does matter what they're asking about. They might be asking for the x values, they might be asking for the y values, or they might be asking for both, in other words, as a point. So those are our steps. So you'll want to have those out as we go through the following problems, because these are the steps I'm going to be following. All right, so let's begin. Example 1a. Identify any relative maxima or minima for this function here. All right, so step 1 is, as we said, to identify any discontinuities. Well, since this is a polynomial, there are no discontinuities. Now, when you guys are doing your own work, you don't necessarily have to write that out. This is just for me teaching you. You do need to at least mentally acknowledge, does this thing have any discontinuities? No? Okay, move on. You don't necessarily have to write this down. But you do need to do that first step at least mentally. All right. The next step is to find the places where f prime equals 0 and where f prime is undefined. So first of all, we need to find f prime. F prime is 2x plus 6. Now we're going to do two things with that. I'm going to find where f prime equals 0. And I also want to find where f prime is undefined. So to do that, we're going to take our derivative, which is 2x plus 6, and we're going to set that equal to 0, and we're going to solve. So if I subtract 6 and divide by 2, I end up with x equals -3. So this is a critical value, right? That's a critical value. Over here, since f prime is a linear function, which also is a type of polynomial technically, there are no places where it's undefined. So there's part B. So there's that number 2. We found our critical values. All right, let's go ahead and move on to step 3. So step 3 is going to look a lot like something we've done earlier this year with the number line test. We're going to put our critical values on this number line. Now I only have one critical value. It was -3. So I'm going to put it right here. So I know that at that point, my graph is either going to have a relative minimum, a relative maximum, or neither. And my goal is to see what is it. And the way we're going to tell is by looking at the slopes. All right. So we could pick anything from -infinity up to 3 in this interval. And on this interval, we could pick anything from -3 up to +infinity. Okay. So step 4, I'm going to do in green here. So we want to pick a number to plug in to our derivative on each of these intervals. So let's go ahead and start with this interval here. From -infinity to -3. Pick a number. It doesn't matter what you pick. Just pick one. So I'm going to pick -5. And then for this interval here, I'm going to pick a number from -3 to +infinity. I'm just going to pick 0. Okay, and we're going to plug those into our derivative. So if I plug that into my derivative, I'm going to get the following. I get -4. And if I plug it in 0 into my derivative, I'm going to get 6. Now, why did we do that? Because that tells us what the slopes are at that point. So what that means is that to the left of -3, I have a negative slope. And to the right of -3, I have a positive slope. Now, step 5, I've actually already kind of started. Step 5 is where we're actually working this stuff out. So I'm going to change these colors here a little bit. So step 5 is where you plug it in. And we see that we have a negative slope and a positive slope. So now if you have a negative slope, that means your function is decreasing. And if you have a positive slope, that means that f is increasing. Now if f is decreasing, that means on the interval from -infinity to -3, it's going in a downward direction. And if f is increasing on the interval from -3 to infinity, that means it's going in an upward direction. Now, since it's going down on the left and up on the right, this critical value, which would go right there in the middle, I'm going to erase that because I don't want you to get confused, but that critical value right there, f of 3, must be a relative minimum. You could tell by looking at the graph. Since it's going down and then up, that must be a relative minimum. So now there is one possible issue with just stopping here. The possible issue is that if this is a discontinuity, then it's not a relative extrema, right? But we should have caught that in step 1. So you got to be careful that sometimes you can have a slope that goes down and then up. It doesn't mean that that's a relative minima, because if it's a discontinuity, it doesn't work. Let me give you an example of that. So suppose that we had a vertical asymptote, right? And on the left of it, it was going down, and to the right, it was going up. Okay? Well, that you don't have a relative extrema here in the middle because there's nothing there. Okay? Or another case would be if you have a hole, right, where that extrema would be. Okay, so you got to be careful. You don't want to just say that f of 3 is necessarily a relative minimum. That first step is pretty important, where we make sure that there are no discontinuities so you don't end up making a mistake. Now, depending on the question, they might ask you to find the answer. So, for instance, do they want the x value? If they want the x value, then the relative minimum is at x equals -3. But if they want the y value, that is f of -3, which is -3 squared plus 6 times 3 plus 10. In other words, just plug it in, right? And that's going to be 9 plus 18, which is 27, plus 10, which is 37. Or they might want it as a point, which is at x equals -3 with a y value of 37. So the answer can be written like this, or like this, depending on what they're asking. Do they want the x value? Do they want the y value? Or do they want the point? And from here, you can tell that since they're asking you to identify the relative max or min, in this case, this would be your actual relative min. Right there. So that's the lowest point on the graph, unless I I think I miscalculated that a little bit. This was supposed to be a -3, so that's 9 minus 18, which is -9, plus 10, which is actually 1. So let me fix that. There we go. My bad. All right. So either way, so maybe I shouldn't have this one boxed either. That way, so we understand that what the question was asking. But these are the 3 different ways you could write your answer. They might say, what is the x value for that relative min? Then you would write it like this. Y value, which is what this one wants, is that. Point is written like this. Just different ways to write your answers. Pay attention to what they're asking for. All right? So here's a guided practice here. So let's go ahead and have you guys do step 1 here. So pause the video. When you unpause it, we'll discuss it. Step 1 is to determine if there's any discontinuities. And once again, since this is a polynomial, there are no discontinuities. All right? Go ahead and pause the video here and do step 2. And when you unpause it, you'll see the solution. From step 2, we try to find our critical values by finding the derivative and setting it equal to 0 and solving, in which case that we get 2 critical values. We also want to look for where f is undefined, but once again, since the derivative is also a polynomial, it has no places where it's undefined. All right, go ahead and pause the video here and do step 3, please. All right, so step 3 is just to make a number line, where we go from -infinity up to our first critical value, up to our next critical value, and then off into infinity. And that gives us basically 3 intervals that we need to test. So let's go ahead and have you pause the video again here and do step 4. Okay, so step 4 is to just pick a number from each interval. So I chose -3, 0, and 4. Now, if you didn't pick those, that's okay. It doesn't matter what numbers you picked. Okay, so just go with what you picked. It's totally fine. All right, let's go ahead and move on into step 5 at this point. Pause the video and do step 5. Okay, step 5 is where you're going to plug these numbers in, -3, 0, and 4, but you're going to plug them into the derivative. Make sure you plug it into the right thing. You plug it into this thing here. So if you plug in -3 to the derivative, you get 6. If you plug in 0, you get -6. And if you plug in +4, you end up with 6. Now, part of step 5 is to also interpret these results, which I haven't done yet. So this is a positive slope, this is a negative slope, and this is a positive slope, which means that f is increasing here, f is decreasing here, and f is increasing on this interval. Okay? And so that means my graph looks like this. It goes up until it gets to -2, and then it goes down until it gets to 3, and then it goes back up again after that. Okay? And what that indicates now is going to help us do step 6. So go ahead and do step 6. Pause the video here, and when you're all done, you'll see the solution. So as you guys can see, just by looking at this little picture I sketched, f of -2 at that point there would have to be a relative max because it goes up and then down. And then f of 3 is at the bottom, so that would have to be a relative minimum. And once again, since it's asking in this case for the relative extrema, that means they want the y values. Okay. Now technically, if you wanted to, you could, I think somehow I ended up on a different slide. Let me go back. Technically, if you wanted to, you could just leave your answer like this. You could leave it like that if you want to, or you could actually calculate it by plugging it in. I'm going to go ahead and just not plug it in just because this already represents the y value, and we don't necessarily need to calculate it. So I think that would be fine to leave it like that in this case. All right, so let's go ahead and have you guys do one now from beginning to end on your own completely. So this time I want you guys to do steps 1 through 6 completely on your own. When you unpause the video, you will see the entire solution. All right, so there's your solution. I'll let you guys study that a little bit. The one thing I would point out here that might not be obvious to you is I went ahead and found the actual y value this time. I didn't just leave it like this. How did I get -11.25? Well, after I found out where the relative minimum is located, it's located at x equals 1.5, you plug that x value into your original function, right? That's what tells you the y value. And so the relative minimum, the y value, is -11.25. Okay, so that's the answer to that one. All right. So let's go ahead and compare and contrast the candidates test with the first derivative test. Just want to make sure you guys got these concepts separate in your mind. They both had to do with finding extrema. Okay. But what's different about them is that the first derivative test helps you find relative extrema, whereas the candidates test helps you find absolute extrema. So that's the conceptual main difference there between them. Now, both of them require you to find critical values. So you have to find where the derivative equals 0 and where the derivative is undefined. Okay, for both of them. But what's different is with these is for absolute values, you plug critical values only into the original function. So that way you can find the y values. Okay. For relative extrema, you plug the critical values not into the original function, but into the derivatives to examine the slopes. okay? But you do eventually plug it into the you plug it into the original eventually. If the question is asking for y. So that's kind of a similarity also. But when it comes to the absolute, using the candidates test, there is no, you don't plug anything into the derivative at all. Okay. Now for the candidates test, we do a little table of values, right? But with the first derivative test, we do a number line test. Different kinds of graphical analysis there. What else do they have in common? What else did you want to, for both of these, you kind of want to examine the continuity of the function. If a function's not continuous on a closed interval, then you can't use the candidates test anyway. Well, you can, you're not guaranteed to end up with an absolute min or a max. With the first derivative test, you want to start off by looking at the continuity to determine whether or not that particular critical value is even worth examining. Okay, so there's another difference. The final thing is that for candidates test, you include endpoints. With the first derivative test, you don't examine the endpoints. In fact, you'll notice on the last two problems, I didn't even give you an interval at all. I just gave you a function. So that means we're going from negative infinity to positive infinity. So we really do have an interval, but you don't include the endpoints of your intervals. So candidates test versus first derivative test, they got some things in common, but they have some fundamental differences. So just want to make sure you guys have that dichotomy in your brain there, because on your test, the questions sound very similar, but they're very different. If the problem is asking you to find absolute extrema, you're going with candidates test. If it's asking for first derivative, you're going with, if it's asking for relative extrema, you're going with the first derivative test. So it's important to know the differences between those two things. So for the remainder of the day, we're going to be just doing more of the same thing, but just kind of, slightly more challenging problems, like this one's trigonometry. This one has a rational function. Just a couple of more challenging questions just to kind of take you deeper into the process. But what you guys have learned today is essentially the idea. Okay, so now we're just going to look at some functions that are a little bit more challenging. All right, so let's consider step one here. Pause the video and do step one. When you unpause it, you'll see the solution. Once again, the answer is none for step one. This is a linear function, this is a sine function, and when you look at your continuity of common functions worksheet, neither one of those have discontinuities. So when you put them together, you still have no discontinuities. So there's no discontinuities at all that we need to worry about. Go ahead and pause the video here and go through step two as much as you can. All right, so here's our answer to step two. I ended up with two critical values, pi over 3 and 5 pi over 3. How did I do that? First thing I do is find the derivative, set that derivative equal to 0, and solve. So there's that, and then you also want to look for where it's undefined, but once again, the derivative has no places where it's undefined because cosine is defined everywhere. All right, step 3. Go ahead and set up your number line for step 3. The trick here is knowing which number goes on the left and which one goes on the right. When you unpause the video, you'll see the solution. All right, so pi over 3 is smaller than 5 pi over 3. Now, how do you know that? Well, it's nice when they have a common denominator because this is 1 pi over 3 and this is 5 pi over 3. And when you have 1 pi over 3, that's definitely going to be less than 5 pi's over 3, right? So getting a common denominator is helpful for these. Another strategy, although I don't really prefer it, is to change them into decimals. But I like this one, just getting a common denominator. You'll also notice on your number line, instead of putting infinity on the left and right, you're going to put 0 and 2 pi. And the reason for that is because they gave us an interval this time. So we end up with 3 intervals that we need to pick numbers from. All right? So for step 4, you guys need to pick a number. And you're going to plug it into your derivative. Okay? Now, we're all going to probably pick different numbers here, but it doesn't matter what numbers you pick, just so long as you pick a number that's actually in the intervals. Okay? And it doesn't matter what numbers you get because all that matters is the sign, whether the outcome turns out to be positive or negative. So when you unpause the video, I'll share with you what I picked. But you don't have to go with that, what I picked. So these are the numbers that I picked. Between 0 and pi over 3, the numbers you would want to pick would be like pi over 6 or pi over 4. You really only have 2 choices on the unit circle. There's technically an infinite number of choices between them, but you want to stick with numbers that are actually on the unit circle. Between pi over 3 and 5 pi over 3, there's a lot of choices. It starts off with 2. You could have picked 2 pi over 3. You could have picked 3 pi over 4. You could have picked 5 pi over 6. You could have picked pi. You could have picked 7 pi over 6. You could have picked a lot of stuff to remember here. You could have picked 5 pi over 4. And you could have picked 4 pi over 3. So, oh, and you also could have technically picked 3 pi over 2. There's a ton of options that you could have picked there between those two values. Next, we have from 5 pi over 3 to 2 pi. You have a little bit fewer options to choose from. You could have picked what I picked, 7 pi over 4, or you could have picked 11 pi over 6. So those are your options. Now go ahead and move on to step 5. And when you unpause the video, you'll see the solutions for that. All right, so there's the outcome. I went ahead and changed things to decimals so it's a little bit easier to see what the signs are in this case. So 1/2 minus radical 2 over 2, you get a negative number. And for the middle interval, you get a positive. And for the right-hand side, you get a negative again. So the graph goes down, up, down, which means that this number here, pi over 3, which would occur right there at that point, would be a relative minimum. And for this number here, it would be a relative maximum. So we have f of pi over 3 and f of 5 pi over 3 are relative mins and relative maxes, respectively, like that. And I'm not going to plug it into the original equation this time just because I'm doing this and I got to actually start my next class. So, but you guys can do that if you wanted to find the y values, and that would be step 6. All right, so we'll move on to the next one. As soon as I'm done with the next class, I'll continue the video. So. All right, guys, let's go ahead and do one more problem now. So go ahead and let's see. Go ahead and see if you guys can do the first step, and when you unpause the video, you will see the solution. So we have a discontinuity at x equals 2. Now that means that we're going to have a critical value there also, but this particular critical value cannot possibly give us a relative min or a relative max, because relative extrema only happen if that point actually exists on the graph. So this, even though it is a critical value, it is not going to give us a relative extrema. So now we're going to move on to step 2. Now, as you guys know, in step 2, we want to find the derivative. And then when we're all done finding the derivative, we're going to set it equal to 0. And then we also want to find out where it's undefined. Right now, at this point, I want you guys just to do one part of step 2. I want you to do the part where you find the derivative, But when you do, I want you to write it out where the numerator is completely simplified. The denominator does not need to be simplified. So go ahead and see if you guys can accurately find the derivative of this function. All right, so here it is. That's what I end up with. Like I said, I wanted you guys to simplify the numerator, but you didn't need to simplify the denominator. Now, we have an option here. Technically, that negative in the front, you could distribute that in which case the top would become negative 4x squared plus 16x. For this problem, it's not really necessary, but you could. Now, here's the next part I want to talk to you guys about. When you're dealing with rational expressions, how do you find where it equals 0? For rational expressions, you could find where it equals 0 by taking the numerator and setting that equal to 0. If you want to find where it's undefined, you're going to take the denominator and set it equal to 0. And the reason for that is because when you have fractions, it doesn't matter what number you have on the bottom. If the number on top is 0, then the answer is 0. Likewise, for a fraction, it doesn't matter what you have on top. If the bottom is 0, that's undefined. So if the top of this rational expression equals 0, that's where the function will be 0. And if the bottom is 0, that's where it will be undefined. So if you want to find where the derivative is equal to 0, all you need to do is set the top equal to 0 and solve. And if you want to find where it's undefined, then you just set the bottom equal to 0 and solve. So I'll pause the video here and let you guys do that. And when you unpause it, you'll see the solution. All right. So setting the top equal to 0 and solving, I end up with 0 and 4. Setting the bottom equal to 0, I end up with 2. Now the 2, I'm going to get rid of that. The reason why I'm going to get rid of that is because we already said up here earlier that's a discontinuity. And even though that is a critical value, because it's where the derivative is undefined, that particular critical value is not going to give us a relative extrema, so we can ignore it. All right. Number 3, let me help you guys out with number 3 as well. Number 3, we're going to put our critical values on there. Now you want to put all your critical values, so let's put 0. We're going to put 2, and I'll explain why we're putting it there, even though it's not one we're going to really care about too much, but you do want to include it on the number line here, and then 4. All right, so I want to test 4 intervals now. Now it's important that let's just go ahead and put a cross through that now, because we know that 2 is not going to give us a relative extrema. It doesn't matter what happens. That cannot be a relative extrema. But we do want to include it on our number line. If you don't, the reason that could cause a problem is because the slope here might be different than the slope here. So if you pick a number that's too far away from 0, well, you might actually end up getting the wrong slope. So putting that critical value in there will guarantee that you pick a number that's in the right region. So you do want to include that critical value that we know is not going to be a solution. Okay, anyway, let's get back down to business here. So now I'm going to let you guys at this point, I'm going to let you guys handle steps 4, 5, and 6. When you unpause the video, you'll see the end of the problem and the final solution. All right, so here's what I got. It goes down and then up, which means that at 0, f is a relative min. And then here it goes up and then down, which means that at 4 it's a relative max. Now you'll notice that at 2 it goes up and then up. So that would mean that there is not a relative min or max there. But you got to be careful. Just because, like technically it could have went like this, right? And I don't want you guys to actually think, okay, it's going up and then down, so that would mean this is a relative max. Why not? Because we already said that can't be a relative max. It doesn't matter that they went in opposite directions. In the same way, let's say that we had some situation like this, where this one went down, and this one also went down. Well, even though this point exists, if the slope doesn't change, then that point would be nothing also. So you got to watch out for those little details. So in order for a point to be a relative extrema, 2 things have to be simultaneously true. First of all, that point has to exist. Second of all, the slope has to go from either negative to positive, in which case it would be a min, or it has to go from positive to negative. Okay? But two things that would cause it to not exist is if that's a discontinuity, or if even though that's not a discontinuity and that point exists, if the slope doesn't change, then that's another reason why it wouldn't be considered to be a relative extrema. But in any event, that's the end of our problem there. We have the relative min at f of 0 and a relative max at f of 4. Now, before you guys turn off the screen, I bet you guys found this to be kind of irritating. That's a lot of numbers to plug into a rather complicated problem. So something that we've done in the past, I'll remind you of, that can make your life a little bit easier here, and it's how to use your graphing calculator. So here's how you would go about doing it on your calculator. The first thing you're going to do is you're going to push y equals. You're going to type the function in there. Now I typed the original function in. There's other ways to go about doing this. You could actually just put the derivative in there instead that we found, but this way would actually be the fastest way to do it. You put the original function in there. You're going to come to second quit, and you're going to go back to the home screen. You're going to push math, and you're going to go down to number 8 where it says derivative, and here you put x. We're taking the derivative with respect to x. Here we're going to put our function that we just typed in, so we're going to push vars. We're going to go over to y vars. We're going to push 1 for function and 1 for y1, and that's the function. If you forgot, it's right here. It's y1 is equal to the function that we just typed in. And then you want to put the value that we were plugging in for x in each of those spots. So I believe we plugged in -1, right? Let's push enter, and it should give you an answer. I have a typo. Let me see what I typed in wrong. Okay, I found my mistake. I think I did what I told you guys not to do many times, which is I got the negative down here mixed up with the minus. But anyway, go ahead and do that. Push enter, and it'll give you the slope right at that point. And then if you want to bring this all up again, just push second entry, and you can put your next point in. Just go back over the -1 here and delete the number you had in there and put your new number in. I think our next number was 1, right? And there's 0.75, and just keep repeating that. The next number I plugged in was 3, and then the next number I plugged in was -5. So it could save you, I'm sorry, +5 I believe it was. Save you a lot of time if you guys go ahead and do that. So once again, you just type in the original function under the Y button, go to your home screen, and then once you're there, it looks like my app is frozen up on me. It did that earlier. You go to math, click derivative, type in all the good stuff, and it can do it for you. Save you a lot of time. But that'll go ahead and close us out for the day. Oh, and by the way, it also shows you a graph of it right here. It's kind of cool. So you can kind of see where the relative minimum and relative maximum would be. Anyway, we'll stop there, and we'll say see you next time and see you in class. Have a good one.